and welcome back to Food Analyst. Today we are kicking off a new series on FSSAI examination. So we are going to discuss some previous year question papers and we are going to explain it in detail. So before we are diving, remember this is just a part 1 of the video. So stay tuned for more videos. So need the PDF of this video? No worry, you can join our Telegram channel and grab the PDF. And our motto is simple. It's simplifying the safety and igniting the knowledge. You can scan the QR codes to find us on the WhatsApp, Telegram and YouTube. So let's get started cracking on this question, shall we? Okay, so first question. Sauerkraut contains what? We have 4 options, 2 to 3% salt, which is constant in all the options. So we don't have to see this well. But the next option is whether it is increase or decrease of acetic acid or lactic acid. So this is the question. The question is simple. We need to say whether it has acetic acid or lactic acid first of all. And we need to say whether it should contain less than 1.5% or more than 1.5%. So let's understand the question, shall we? So what is a sauerkraut? Sauerkraut is it's a fermented cabbage basically, and we will say that as Brassica olyrica. Okay, so there is a federal definition for this specific sauerkraut, that is, it should be clean, sound product and characteristics flavor, and it will be obtained only by the full fermentation. What does that mean by that? See, once it is fully fermented, it has not less than 2 to not more than 3% of salt will be there, and along with that it also has not less than 1 and 1.5% of acid. What acid? It is lactic acid. So they have given 2 to 3% of salt, and obviously 1 and 1.5% of more than, here the word is important, not less means more, right? So more than 1.5% of acid, which is lactic acid. And sauerkraut which has been rebrined, if you are rebrining it, like for example for a process of canning or repacking, then it should not contain less than 1% of the such acid. That's it. So let's see these things. So salt, it has to be 2 to 3%, done. Lactic acid should be greater than 1.5%, done. So the answer should be B. Okay, but let's learn more about this product, shall we? So temperature, what should be the proper temperature? It's 15 degrees Celsius. And the compound contribute to what are the flavors? See, obviously we have a distinct flavor for the sauerkraut, and that flavor comes from lactic and acetic acids primarily, followed by ethanol and volatile compounds such as diacetyl and acetaldehyde, acetyl, isoamyl alcohol, N-hexanol, and then ethyl lactate and ethyl butyrate and isoamyl acetate. These are not that much important, but the primary flavors will come from either the volatile compounds or lactic or acetic acid. Now let's understand the fermentation process, because that's what the product makes, right? So what is a cod fermentation? How this fermentation started? This fermentation is started by Leuconostoc mesenteroids. See, this compound is not the very first compound which attacked the let's say cabbage. This compound is the first compound which outdone all other microorganisms. So the very first microorganism which thrives in the let's say fermentation is Leuconostoc mesenteroids, which is a heterofermentive lactic acid bacteria. Okay, so we'll discuss what is a heterofermentive lactic acid bacteria in next classes. But just let's understand that it's a heterofermentive lactic acid bacteria, and it destroys all other bacteria. See, the point is important. It destroys all other bacteria and promote the lactic acid producing bacteria, right? And this first step of fermentation itself will produce 0.7 to 1% of acid. Okay, so the first step itself will produce 0.7 to 1% of acid. Okay, this is the first step. And the first step itself will create that much of acid. But that is not enough to say this product as a sauerkraut. That's why we need to proceed it further. And along with the lactic acid, which has been produced 0.7 to 1%. It also contains acetic acid, ethanol, mannitol, dextran and esters. Okay, so see, this mannitol and dextran, it's a bitter flavor component. So we need to further utilize this component. In order to reduce the bitterness, we have to use this component and we have to convert these components, right? So this is the second step. We have to utilize these components. Okay, so let's go further. What is the next step? Next step is obviously it promotes other lactic acid bacteria, right? So Lactobacillus brevis will come, which is also a heterofermentive, and some homofermentive bacteria, like fermentive bacteria like Lactobacillus plantarum will also come. But the major bacteria which comes after this Leuconostoc mesenteroids is the Lactobacillus plantarum. Okay, even though brevis will also come, the majority of the bacteria will be Lactobacillus plantarum. But there is a slight twist. If the salt is increased, or if there is any like misconception, then Pedicoccus cerevisiae may also acquiesce. And similarly, Streptococcus faecalis is also will also come if the salt is too much high, like above 3.5%. Okay, this is also produce lactic acid only. So these two components will sometimes come, Pedicoccus and then Streptococcus. We'll study this detail later on, but let's understand this. Okay, then let's go further. This Lactobacillus plantarum will continue producing the acid. What acid? Lactic acid. So, and it will raise the acidity to 1.5 to 2%. Now see, the desirable lactic acid content, even though it is actually only 1.5%, most desirable is actually 1.7%. They might ask this question also. So the most desirable value for lactic acid is 1.7%. So this specific Lactobacillus plantarum will produce to the range 1.5 to 2. Okay, and see, this bacteria will also utilize the mannitol. So if it is utilizes, obviously the bitterness is going to reduce, right? This will reduce the bitterness. So that's it. Now we have achieved the end point which we needed, like 1.5 to 2%, and the fermentation can be stopped at the stage by either using a principle called canning or refrigeration. That's it. So this is a simple fermentation of sauerkraut. I hope you have understood the whole process, and the answer is 2 to 3% of salt, and you know now why it is 1.5% lactic acid. Okay, so let's move on further to the next question. The process of preserving food by rapid freezing followed by the dehydration in vacuum is called what? And they have given 4 options: dehydrofreezing, cryopreservation, lyophilization and cold sterilization. So ignore all these things. The answer is actually lyophilization. And lyophilization, another name is actually freeze drying. Okay, so the another name of lyophilization is actually freeze drying. So let's understand this process. First of all, preservation of food product, right? So how we the drying is the most used preservation earlier, right? And the drying is achieved by what? We'll use heat, and during this heat, when we use the heat, the moisture of the product will be removed. Okay, so that's how we will preserve the food by drying. But what happens if any heat sensitive food which we are using, it likely to get damaged. So that's why we need to do something different. We need to do a drying method which does not involve much heat. So that's where the freeze drying comes. Okay, so the freeze drying is actually called as lyophilization. It's a process of preserving the food products by freezing them and then evaporating the water, which is in the form of ice. Actually, after freezing it will be in the form of ice, and it will directly go into an vapor by a process called as sublimation. So let me explain this, don't worry, it's simple process only. So the freeze drying has 3 steps. First step is obviously freeze drying means freezing, right? So we need to freeze the product. So what happens if this is a product, all the moisture present in the product will freeze. Okay, so this is the first step. If you are doing this the freezing in a very quick way, then small crystals will form. Small ice crystals will form. If we are doing this in a very large amount of time, then large crystals will form. Simple, right? So this is the first step. Okay, now you have freezed it. What is the next step? It is primary drying. Okay, that is the second step, and the third step is secondary drying. Let's see this in detail. First, we have already freezed it. The product of the frozen, first the product is frozen so that the water contained in it become ice. Okay, now the product is actually ice. Okay, that's great. Now the second step is we need to vaporize this ice directly into an air, or let's say a gas. How to directly vaporize it? By using a concept called as sublimation. Okay, so you might be wondering, how is this even possible, right? So this is possible by one concept called as triple point of water. Triple point of water. So in this triple point of water, all the three stages of water, like solid, liquid and gas, will be existed. So it's easy to push from one state to another state without skipping the with skipping the one or two steps. Okay, so ignore the point of triple point of water as of now. Just understand it has the same concept, like triple point of water, the concept of triple point of water is behind the process of sublimation. So that's what you need to know. We'll discuss this topics further in some other classes, but as of now, the principle is simple. The principle is actually sublimation, and sublimation works on the triple point of water. Okay. So the next thing is in the first let's say there are three steps, right? In the first step it becomes ice. In the second step, because of the sublimation, it has been evaporated. Does that mean the product is actually freeze dried? No. Not all the water in the product is actually evaporated. So we need to do a third step. The third step is actually nothing but a secondary drying, or we can say it is a desiccation drying. So it will eliminate the water which are not converted into ice. Okay, so this water will directly be vaporized. So now the product which has been completely dried, okay, all the water present in it, whether it is in ice form or the normal water form, both are evaporated. So that is the principle of freeze drying. So we are not using much heat because we are doing a freezing, and after freezing we are directly converting that into a gaseous state. So that's why it's a freeze drying. And the principle of freeze drying is sublimation, and sublimation works on triple points of water. So that's how we need to connect the dots. So that's it. So now you know the answer. Rapid freezing followed by the dehydration in vacuum is actually that's actually lyophilization freeze drying. Okay, so let's move on to the third question. So third question is the complete active enzyme. Okay, the complete active enzyme containing both protein and non-protein part. So what is they are simply asking a definition of set. You need to know all these things. What is an apoenzyme, cofactor, enzyme and whole enzyme? Don't worry. So let's quickly discuss this. Enzyme is a biocatalyst, which means it will catalyze the biochemical reaction both in vivo and in vitro state. Okay, and it is also a colloidal. Okay, and it's thermoliable, which means it has been affected by heat. If you give heat, you can stop the enzyme process. And it's also specific in action, which means certain enzyme will only work on certain places. You cannot use every enzyme into every steps. It is very specific. Okay, then next point. All the enzymes are invariably proteins. Only there are few RNA molecules which they can claim as an enzyme. One of such thing is riboenzymes. Okay. So now comes the important part. There are many enzymes which also needs an additional cofactor. Okay, so enzyme plus cofactors will ultimately complete a catalytic activity, because the enzyme itself is not enough. They need an extra factors, cofactors. Okay, this cofactors can be anything, any organic molecule. Okay, any organic molecule, or it may be metal ion also. For example, I have given few examples: iron, magnesium, zinc and magnesium and all. manganese and all. Okay, so now comes the important part. See, as I told you, enzyme enzyme needs a cofactor. Okay, so we can say enzyme is a protein part, right? So that protein part is called as apoenzyme. Okay, the protein part is called an apoenzyme. So how we can write is, I can write apoenzyme, okay, plus this is a protein part. Okay, so I'll write this as a protein part, and I am adding this with a cofactor, right? So now I am adding this with the cofactor, which is an, obviously I can simply say this is a non-protein. This is a non-protein, or here it's mentioned organic molecules, so it can be organic molecule or it can be metal ions also, anything. Okay, so this will ultimately give a complete enzyme. That complete enzyme is called as whole. Let's remember this as a whole. Okay, holo enzyme. So this holo enzyme is the most active enzyme which will be used for the process. Okay, so this holo enzyme is an active enzyme. This is a complete enzyme. Okay, so the question is basically this: a complete active enzyme containing both protein and non-protein part is what? It's holo enzyme. But we should not stop there. We should learn more about these things, right? So let's go further. When a coenzyme, which is or metal ion, whatever it is, if it is tightly bonded like a covalent bond, same like the coenzyme, I am writing that as a co, and protein part I am writing it as a PO. If this bond is happened with a covalent bond, which is a strong bond, then this specific group is called as prosthetic group. Okay, you might be wondering like what is the difference? The difference is simple. If the coenzymes can be easily separated from the enzyme by dialysis, here we can easily separate the coenzyme or cofactor, right, by dialysis. But here this specific prosthetic group we cannot simply separate by dialysis. It cannot be separated easily. And most of the enzymes, coenzymes which we can see here are vitamins. You can see here vitamin B7, B12, B2, B3, B5, B6, B1, B9. All these vitamins are acting as a precursor, which means this vitamin will ultimately give this coenzyme. Okay, and this coenzyme will come and attach with a specific enzyme, and that enzyme will work on a reaction. So this is the whole process of how a vitamin will ultimately help in every enzymatic activity in our body. Now you have understood, right? So you can read these things. Like one of the important is biotin, biocytin, and it's important for catalytic activity. If there is a reaction which requires transfer of CO2, then we need this biocytin coenzyme. And this is also important, thiamine pyrophosphate, which we say TPP. Okay, coenzyme A is also come from the vitamin B3, which is pantothenic acid. So just go and study all this table. And also I have included this also, like metal ions and its enzyme name also. Okay, for iron it is catalase, peroxidase and cytochrome oxidase. So these are the specific metal ions and these are the enzymes which is attached to it. Okay, so the specific metal ions will be attached to the specific enzyme. So this we can say as a cofactor or coenzyme. So this is the protein part of an enzyme. Okay, or we can say apoenzyme. Okay, that's it. Let's move further. I think I have answered the question. It's holoenzyme. Okay, let's go further. TSS content of squash. Okay, so this question is pretty simple. If you have read the FSSAI regulation, it's pretty easy. The fruit juices which does not undergo the alcoholic fermentation is called as unfermented beverage. Simple. So what are the unfermented beverages? It's called natural or sweetened juice, RTS, nectar, cordial, squash, crush, syrup and fruit juice. Okay, and even fruit juice powder, we can say that it is a non-alcoholic. Okay, even barley water and carbonated beverage also come under this group only. Okay, so squash is basically prepared from the fruit pulp or juice. It is very much cloudy. You can see this is a squash which is very much cloudy. Okay, so we need to dilute before drinking. And see, since this itself a cloudy, we don't need to do the clarification step. But cordial is an opposite of the squash, because here we need a clear juice and everything else is same. Okay, everything else is same except if it is a clear juice, it's cordial. Okay, if it is a clear juice, it's cordial. If it is not a clear juice, it's squash. Okay, next. As per the FSSAI food product regulation, so like ignore the spelling, food products regulation 2023. So squash has a minimum fruit percentage of 25. All the squash, crush, cordial, even barley water, everything has, this is the amount of food like fruit juice which is present in the product, which is 25. But the question which is asked is TSS, total soluble solids. So that is 40 for squash, 55 for crush, fruit syrup is 65, and cordial and barley water it is 30. And here, except the barley water, all the other acidic content, citric acid content is 3.5. See, in this video itself, we have learned two citric acid related things. One is, lactic acid related component will be there. That is, we have seen as 1.5. Here 3.5 citric acid content for certain fruit juices related products. Okay, this is important. Except barley water, all of these are 3.5. This is actually a recent version. Okay, so you can definitely study this. See, the TSS is important. See, the for squash it is 40. So simply the answer is B, 40 to 50%. Okay, let's move on further. Okay, they are asking a FDA approved non-nutritive sweetness, which is 2000 times sweeter than the table sugar. We need to identify what is that sugar. Okay, so to solve this simply, we need to know first is what is a non-nutritive sweetener, right? Sweetness are sugar substances such as aspartame, sucralose, stevia, which is derived from an ingredient, right, to sweeten, and that ingredients will give the flavor to food, right? The use of this specific components like aspartame, sucralose, stevia is actually suggested because it is much sweeter than the sucrose. Okay, this will give the enormous amount of sweetness. So that's why the people will use this. And also one more thing is, for example, sweetness contribute only a few to no calories. So it will not raise the blood sugar level. And some people will also use this for weight, to stop the weight gain and all. Okay, that has been debatable, but this is basically the whole concept behind the sweetness and how it is used. Now let's first of all see the sweetness intensity compared to table sugar. We can say advantamine is the highest one, which is 20,000 times sweeter than the. So this is compared to the normal sugar, which table sugar, which means sucrose. Okay, so this is compared to sucrose. So as you can see, this table itself I have taken from the FDA website. So they have asked the question from this table only. Okay, so the range of sweetness. See, sometimes it has a range. For example, it's Tau Martin, it is 2000 to 3000, neotamine 7000 to 13000, saccharin is 200 to 700, sucralose is 600, and stevia or stevia glycosides is 200 to 400. See, the stevia is a plant sugar, remember it. And then 100 to 250, it's actually nextries or monk fruit sugar, 100 to 250. Aspartame is 200 and acetylcholine is 200. Okay, so remember, all these values are important. Every single term is important, especially this aspartame, acetylcholine and advantamine. See, most of the people will simply study these things, sucralose, aspartame, acetylcholine, but they have asked advantamine, which is the very first compound. So the answer is actually C, advantamine, right? Which is 20,000 times sweeter than the table sugar. But let's understand some other things also. I haven't explained it well, so let's deeply understand this. What is a non-sugar sweetness? Non-sugar sweetness, which means NSS, are widely used as a food additives. They're classified as a caloric sweetness and non-caloric sweetness. Okay, so non-sugar means not sucrose. All other sugar except sucrose is considered as an NSS, non-sugar sweetener. Okay, and it is divided into calorific sweetness and non-calorific sweetness. Calorific sweetness means as this term is as per the FSSAI. All these terms is given by the FSSAI itself. Every single word here is given by FSSAI. So you don't need to worry, all the words are important. Substance which have greater than 2% of calorific value is considered as a calorific sweetness. Substance which have less than 2% of the calorific value is called as non-calorific sweetness. They have given example. All the sugar alcohols and then maltitol and syrup and lactitol, xylitol and all, it's actually calorific sweetness. And in case of non-calorific sweetness, we have erythritol. This is the exceptional. Okay, and stevia, taumatin, aspartame, sucralose, neotame, acetylamine, aspartame, and then saccharins. Okay, so these are non-calorific. See, this value is important. This is less than 2%. This is greater than 2%. Okay, this definitely can be asked in some questions. Next question. Ideal refrigerator storage temperature for perishable food is given what? And we have 4 options: 1 to 4, 1 to -4, -4 to -8, -6 to -24. See here, it's a refrigerator storage. So ideal refrigerator storage, they have been asked for freezing storage temperature. It's a refrigerator storage for perishable food. Okay, so let's understand this. This table is also created from an FSSAI website. So obviously this table is actually created by carefully analyzing the FSSAI's licensing regulation. Okay, if you went to FSSAI licensing regulation schedule 4, you can find so many content related to different types of catering or different kinds of food industries, right? So each and everything has a definite values which is mentioned in it. So I have made a table. This is actually from a book, from a food catalyst book only. We are currently making it. So from that book I have taken this specific the specific flow charts. The specific table. So the question is, for ideal refrigerator storage, what is for perishable food, what is the temperature? So here we have to see the chilling food, or we can say refrigerator storage also. So receiving a temperature of potentially high risk food. For high risk food, it should be below 5, which means 4. Okay, 1 to 4. Below 5 means 1 to 4. See, for freezing, the temperature should be -18. Okay, -18. For cooling, chilling, it's below 5. Okay, and I have given all other temperatures also, which is also really important. For example, temperature for washing the utensils is 43 degrees Celsius. To make a cooked food, you need to have the core temperature of the food should be 75 degrees Celsius. Okay, and the time should be minimum 2 minutes. The center of the food should be at 75 degrees Celsius with a minimum 2 minutes. And to thaw in a refrigerator, it's 1 to 5 degrees Celsius. Running water, it's 15 degrees Celsius of maximum 90 minutes we can do. Reheating the food, you have to reheat for 74 degrees Celsius for minimum 5 minutes. And reheating in microwave should be done in 75 degrees Celsius for minimum 5 minutes. Chilling of the food should be done in 5 degrees Celsius. Freezing done in -8. If you are cooling a food, for example, you wanted to chill a food and you have to keep it in the refrigerator, what you have to do is you have to reduce the heat of a food from 60 degrees Celsius to 21 degrees Celsius within 2 hours. Then from 21 to 5 degrees Celsius within 4 hours. If you have maintained this cycle, then you can keep the food in the chilling. If you cannot able to maintain this, you have to do is you have to keep it above 60 and you can keep it for 2 hours. Okay. Cold holding food display. If you are not done anything, then you have to keep the food at 5 degrees Celsius below 2 hours for 2 hours. Okay. So to wash the dishwashing machine, the 60 degrees Celsius is the approx temperature. and the final rinse temperature is 77 degrees Celsius. Okay, in the dishwash. So these are some of the values which I have taken from the schedule 4, plus also there are many manuals given in and 4-stack training courses I have taken. So all of the things I have combined it and made this table. You can also see this tables in many 4-stack courses also. So that's it. And here the answer is simple. It's actually 1 to 4 degrees Celsius. Okay. So next question. Type of packaging materials which is hard, moisture resistant, low gas permeable and high impact strength. So let me tell you. So there is a concept in packaging material which is actually the concept is actually pretty simple, that we need to stop the gas to go outside or come inside, and we need to stop the moisture from go outside or come inside. Okay, so to stop the gas, it's called as the permeability of gas, and to stop the moisture, it's also called as a permeability of moisture or moisture resistant. So this is one of the important two properties in a packaging material which we needed basically. Okay, so that's why this is an important question. And and apart from these two, they have mentioned one more property. That property is it's really hard. Okay, whatever the packaging material they are mentioning, it's really hard, and it has a high impact strength, which means you can force it, nothing will happen. So it has a high impact strength. So option is polyethylene, polypropylene, polyvinyl chloride and polystyrene. So let's understand this. Plastic materials is actually solid at an ordinary temperature, right, in room temperature, which allows appreciable and permanent change of the form without losing its core. It's just a simple definition of plastic which is mentioned in the general books. Okay, so with heat and pressure you can demold it and change it into multiple forms of plastic. Okay, basically this plastic will be divided into these 5 forms. One is polyolefins. Under polyolefins we have PE, polyethylene and polypropylene. Under polyvinyl group we have PVC. And under the condensation we have PET and nylon, which is a polyamide. Under the styrene polymer we have polystyrene and expanded polystyrene. And finally carbonate group we have polycarbonate. So these are the important polymerist films which we are using in the food packaging. Okay, so the question is actually simple. We need to find which packaging material which is hard, moisture resistant and low gas permeable. So polyvinyl chloride, which is also hard, which is low GTR. G means gas transmission ratio. Gas transmission rate. Simply, as I told you, there are two principles. That low gas permeable means getting inside, right? So GTR, if it is low GTR means low gas transition rate, and moderate, this is water vapor transmission rate, WVTR, GTR and WVTR. WVTR means water vapor transmission rate. So it has a moderate GTR and then moderate WVTR and low GTR. Okay. And it's also like glass, which means very ductile, good mechanical strength, retention of flavor, excellent printability, and so on. But the question is hard. There isn't many material which we can say really hard. So that's why this is an easy choice. The word is really important, because many material has moisture, low gas permeable is there, but the high impact strength and hard, which actually differentiates this from all other products. So the answer is the polyvinyl chloride. Let's move on further. Texturized vegetable protein, TVP. This is actually very famous concept in the food industry right now. So what it is made from? It's actually soya bean, wheat, oats or all of the above. So basically it's simple. Texturized vegetable proteins is actually made from soya protein only. 50% of compound will be soya protein. But we cannot make only with that. We can make it with cottonseed, wheat or oats as well. Okay, so how it is created is actually, first we need a defatted soy flour, which means we are removing all the fat which is oil, and whatever the defatted flour is there, like the remaining the waste, or which we can say anything, that defatted soy flour is actually blended with water, vitamins and flavors and colors, and then cooked. And once it is cooked properly, we are extruding that by using the process called extruding, and the instrument called extruder. At an elevated temperature, we can pressure and finally force the food through a subtle dye. For example, the nuggets, the soya nuggets which we are getting in the markets, which is actually formed from a dye. By compressing the cooked food into the dye, it will create the small balls. But you need to remember that this TVP has to be rehydrated with water before using, because it's already cooked and it has to be rehydrated to properly use it. Okay, so we can shape it into chunks, flakes, nuggets, grains or strips, and different sizes based on the nozzle which we are giving. So that is the textured vegetable protein. And this name is actually given because usually the protein compounds in the meat has a texture in it. So to replace the meat, we are using the TVA as a meat replacer. There are many like the meat gimmick compounds are coming, that is actually prepared from the TVA only, texturized vegetable protein only. So the answer is actually all of the above. We can made it from soybean, wheat and oats. Here it's given, even cottonseed flour. Okay. So next question is, garlic contains an active compound which acts as an antimicrobial agent. So what is that agent? I have given allicin, limonene, cymin and anethol. So basically there is a concept called phytochemical. This is actually present in many of the ingredients which we eat currently. But not all the phytochemicals has an antimicrobial agent. So first let's see that. See here, as we can see, there are many, like for example take ginger. It has many chemical constituents which is phytochemicals. Gingerol is there, and then shogal is there, and then gingerodone, citral, and then gingerone, and then beta phenylenedione is there. So there are many chemical compounds. For black pepper, it is pepperine, and then beta caryophyllene, and then limonene, and then carine, and then mycene, and then trepilinone. There are many compounds out there. Under turmeric, we have curcumin, which is really important. For cardamom, cineol, and then also linalool. And for garlic, it is diallyl disulfates, diallyl disulfates, azone and allicin. Allicin is there, allin is there. Okay. And then for clove, it is eugenol, and then some component of beta caryophyllene is also there. Fennel is estradiol, and then trans anethol. See, the anethol is actually for fennel, and cinnamon, it's actually cinnamaldehyde. So all these things are phytochemicals. But which phytochemicals has the antimicrobial activity? That we need to know, which means it can act against antimicrobes, right? So garlic has allicin, or it can also called as thiosulfonates. Okay, ginger has gingerol and paradol and shogal and gingerone. All these things has antimicrobial agent, act as an antimicrobial agent. Black pepper is actually contain pepperine. Turmeric contain curcumin, clove contain eugenol and cinnamaldehyde. See, not just cinnamon, even clove contains cinnamaldehyde. Okay, fennel has trans anethol, and then methyl chaviol and fenchone, and then cinnamon is cinnamaldehyde. Onion, it is quercetin and allicin. So these are the different components which can act as an antimicrobial agent. So in this question, they have asked for garlic, which is allicin. That's it, simple, right? So let's move to the next and final question. In the pulse milling, mixing with the red earth is known as what? Okay, this question is actually pretty simple, but many of the students haven't written it well. Let me tell you why. Because if you have read a book from the ICAR website, they have given a detailed instruction of how to do the milling. So in that specific book, they have given different types of milling for different products, right? For pulse milling, they have given 3 types actually. One is actually wet milling, dry milling, and then commercial milling, and then home milling. Okay, so So here they have given two things only, wet milling and dry milling. So in that wet milling, there is a concept called soaked pulses mixed with the dry earth. Dry earth is nothing but the red soil which we see usually. It's just a red soil, that's it. Just it's a clay red soil. Okay, they will add some water into the red soil and they will mix it with the grains, soaked grains. Okay, for 3 to 12 hours they will soak the grains, then they will mix it with 5% of this the red soil or red earth, whatever it is. Then they will keep it for overnight and they will let it sun dry for 2 to 4 days. After it's sun dried, see, this soil has a specific property. It will easily lose moisture. If you are from a red soil like I am from the south of Tamil Nadu, so I can see many red soil here. Even after rain or something, the soil will be easily lose its moisture. It will quickly drain out all the water, right? So that's why this is used as a process to quickly drain out the moisture from the food, moisture from the pulses. So once it has been properly dried, by the process of sieving, this red earth has been separated from the pulses. That's it. Okay. So this process is actually used for the wet milling, wet method milling. Okay. And why we are using red earth? To facilitate the increase in the rate of drying and loosening the husk. Okay. So that's it. So that's it. So the answer is actually pretty simple. The answer is wet milling. So the red pulse milling mixed with the red earth is actually wet milling. Wet milling, or we can say wet milling of pulses or whatever it is. So that's it. See, here is the flow chart of the process which I am talking about. So after soaking 3 to 5 hours, we are mixing this with the red earth of 5%. And see, here conditioning overnight for moisture. Conditioning means adjusting the moisture in a perfect level. Okay, so we are doing a sun drying and tempering for 2 to 4 days, and after the sieving process we will remove the red earth. Okay, then we will de-husking, splitting, sieving, dal. I'll do the usual steps, but this is the whole flow chart of how the process will run. So that's it. That's it for the video. We'll release the part 2 in a few days, and make sure to give a like to this video and subscribe the channel, and make sure to join our channel. We are conducting a free daily quiz every day at 7 p.m. So every day there will be a different topic and we'll be conducting different quizzes. So make sure to join the Telegram channel, okay, and make sure to join the YouTube channel also, so that you can continue the series.